The universe has this hidden architecture. It's on a scale that's hard to picture. It's not just stars scattered randomly. The cosmos is organized into these immense, coherent structures. Vast walls and voids, and they hold the key to everything. The fundamental forces built the largest things in existence, but the biggest structures we see. They might challenge the laws of physics. A faint whisper from the Big Bang grew into a web that holds 1,000,000 galaxies, and you start to see the universe not as chaos, but as this grand, interconnected design. We're like an ant on a blade of grass trying to map a continent. From Earth, the night sky is just a flat sheet of glittering dots. For most of history, that's all we had. We couldn't tell if two stars that looked close were actually neighbors or strangers separated by huge gulfs. To see the universe's real shape, we needed new eyes. We had to learn to measure depth. That breakthrough came from understanding light and the distances it travels. The basic unit for this new map is the light year, how far light goes in 1 Earth year. Light is the fastest thing there is. It moves at about 300,000 kilometers every second. In a year, that's nearly 10 trillion kilometers. Now, the closest big galaxy to us, Andromeda, is about 2.5 million light-years away. The light we see from it tonight began its journey when early hominids were just starting to walk in Africa. We're not seeing the universe as it is, we're seeing it as it was. That's the first big shift. We're cosmic archaeologists looking at fossils made of light. For the truly huge scales of the largest structures, astronomers use an even bigger measuring stick, the megaparsec. 1 megaparsec is about 3.3 million light-years. It's a unit born from necessity because saying billions of light-years every time gets cumbersome. But knowing distance is only half of it. The real revolution was learning to see in 3 dimensions. That's where redshift surveys come in. When a galaxy moves away from us, its light waves stretch, shifting toward the red end of the spectrum like the fading whistle of a train moving away. By measuring that redshift, we can calculate how fast the galaxy is receding, and because the universe itself is expanding, how far away it is. Imagine a photograph of a city at night, all the windows just points of light. Then you magically gain the ability to measure each light's exact distance from you. Suddenly, that flat picture explodes into a rich, 3-dimensional model. You can see which lights are in the same skyscraper, which are in buildings blocks away, which are lone lamps in distant suburbs. That's what redshift surveys did for the cosmos. They turned the sky from a beautiful tapestry into a deep, 3-dimensional map. This map is the fossil record of the universe's growth, a snapshot from its adolescent years. Every dot of light is placed not just on a sphere, but at a specific moment in cosmic history. With this map, we could finally step back and see the pattern. And what we saw wasn't random. It was a web, a vast, intricate, shockingly organized cosmic web. Now, with these new eyes and this new map, we're ready to meet the titans that form its threads and nodes. That 3-dimensional map showed a pattern. It wasn't random. It was a structure, an architecture. The universe on the largest scale we can see forms a cosmic web. Like the foam on a beer or the connections in a brain, that's the shape. There are these dense threads of galaxies like strings of light. They twist and connect. And they surround huge spherical voids. These voids are almost empty. They can be hundreds of millions of light-years across, with just a few isolated galaxies inside. The web is the skeleton, the voids are the space between the bones, and all of this comes from a whisper. Right after the Big Bang, the universe had tiny ripples. Quantum ripples in density. Some spots were slightly denser than others. Gravity took those tiny imperfections. Over billions of years, it amplified them. It pulled matter toward the denser spots, so the dense regions got denser. The empty regions were left behind, but gravity pulls in all directions, so the matter didn't just collapse. It flowed along lines, it formed the walls and the filaments. The strange thing is, the main thing that built this web is invisible. It's dark matter. We can't see it, it doesn't interact with light, but we feel its gravity. The thinking is, dark matter made the first scaffolding, the invisible frame. Then normal matter, the gas, the dust, the stuff that makes us just flowed into those gravitational valleys. It lit up the structure like dew on a spider web. And this web isn't static, it's dynamic, it's evolving. The filaments are like rivers, galaxies flow along them toward the intersections, the nodes. And at those nodes you find the most massive gatherings, the true titans of the universe. At the cosmic web's intersections, you get its biggest gatherings. The Coma cluster, for example, it's not just one galaxy, it's thousands packed together. Their gravity is so strong, it's actually stopped the universe expanding inside that region. That's a galaxy cluster, the most massive thing gravity can hold together. Like a city of galaxies, they're so close, their gravity has permanently beaten the expansion. They orbit a common center, they're locked in that dance forever, but it goes bigger. Just like cities are in nations, clusters gather into superclusters. We're in one, the local supercluster, Laniakea. It means immense heaven. A supercluster isn't gravitationally bound, though, it's more like a vast river. A flow of galaxy clusters and groups and isolated galaxies, all moving in the same current of the cosmic web, even while the space between them stretches. It's a temporary metropolis, a dense knot that will eventually be pulled apart by the expansion. How these things form is a story of accumulation, hierarchical clustering. Early on, you had small clumps of dark matter and gas. Their gravity pulled in nearby material. They started to merge, like small streams becoming a river. Over billions of years, these protoclusters collided. They combined. They built up into the massive clusters we see, and then those clusters became the building blocks. Drawn along the web's filaments toward common centers, assembling the sprawling superclusters, it's a bottom-up construction, orchestrated by gravity. It's been going on since the first stars, and still, for all that size, clusters and superclusters are just parts of a larger pattern, threads in a tapestry. The universe's true skeleton. The map was finished, the pattern was clear, but the people who made it weren't ready for what one line of data would show. In the late 80s, two astronomers, Margaret Geller and John Huckra, were mapping a section of the northern sky. They used redshift. They plotted thousands of galaxies in 3 dimensions. Theory said they should see a gentle, lumpy spread, but their data showed a cliff, a dense, towering mass of galaxies that just kept going. This wasn't a cluster. It was something different, a vast flat sheet. They named it the Great Wall. At the time, it was the largest single structure anyone had ever seen, a filament of the cosmic web, visible. Over 500 million light-years long. Light would take 500 million years to cross it. Our whole local supercluster would just be one neighborhood on its surface. The find shocked cosmology. The models said matter should be fairly even on that scale, like flour mixed into batter. The Great Wall wasn't a lump, it was a mountain range. Its existence meant the universe was lumpier, more structured, more dramatic than anyone had proposed. It was the first direct, spectacular evidence for the cosmic web. It proved galaxies weren't just random or in small groups. They could form into titanic architectures. This one structure forced a complete recalibration. It redefined scale. The universe suddenly felt more immense, more intricately designed. If a wall that size existed, what other giants were out there in the dark? The Great Wall wasn't an anomaly. It was a signpost, a declaration that the cosmos was built on an epic framework. and as our surveys got wider, deeper, we'd find it wasn't even the largest. The Great Wall changed things, but it was only the start. Our maps of the universe still had these huge empty spaces, unknown places. Then a different kind of telescope started watching. The Sloan Digital Sky Survey. It began in the year 2000. It was an automated digital system. It wasn't just looking at interesting spots, it was photographing everything. Cataloging millions of stars and galaxies. It was taking a census, and in all that new data, astronomers found another giant. They named it the Sloan Great Wall. A filament in the cosmic web, so large it's hard to really think about. It stretches about 1.4 billion light-years. To understand that, imagine a beam of light. The fastest thing there is. It leaves one end of this structure back when the first complex cells were forming on Earth. That beam of light would only just be reaching the other end now. Today, our entire local supercluster, with all its groups of galaxies, is just a small knot. One knot along one of its many strands, and compared to the earlier Great Wall, this one wasn't just bigger. It was more detailed, a denser network of filaments and clusters, a real backbone for the universe's large-scale structure. Finding it was only possible because of these new automated surveys. We weren't sketching with a pencil anymore. We were using a broad digital brush covering a full quarter of the sky, and that gave us a more complete picture. A more startling one, the Sloan Great Wall did more than set a record. It challenged a principle. Cosmology has this basic idea. On the very largest scales, the universe should look about the same everywhere. It should be smooth, homogeneous, but a structure 1.4 billion light-years long. That tests that idea. It pushes right against the theoretical limit of what our models say is possible. The seeds for this giant were planted at the very beginning. Those quantum ripples from the Big Bang stretched across the early universe. They were the blueprint. And then gravity worked for billions of years, pulling those slight over-densities into these immense walls of light and matter. The Sloan Great Wall is a fossil from that primordial time. Grown to an almost impossible scale, it showed us our catalogs are never finished. Every new survey, every deeper look, shows a universe more grandly structured than we thought. More mysterious, and if this was the limit, what happens when we find something that seems to step right over it? The web is shaped by what's missing, just as much as by what's there. For every great wall of galaxies, there's an emptiness on the same scale. These are the cosmic voids. If the filaments are like mountain ranges, the voids are the deep ocean trenches. They're the negative space. It's what gives the web its shape. And to understand the structure of everything, you have to understand the structure of nothing. The most famous one is the Boötes void. It was found in the 1980s. From here, it's near the constellation Boötes, but it's not just a dark patch. It's a spherical chasm, about 330 million light-years across. To put that in scale, if the Milky Way were at the center, the nearest edge would be over 150 million light-years away. In every direction, in that whole volume, astronomers have only found about 60 galaxies. You'd expect thousands. It's a cavern, profoundly lonely. The few galaxies inside are called field galaxies. They're like solitary islands in an ocean of darkness, cut off from the busy galactic cities. Their isolation means they evolved differently. Often quieter, older, they miss the mergers, the collisions that drive star formation elsewhere. It's a haunting thought. A civilization born there would look up at a night sky almost empty of neighboring stars. The cosmic web would be a distant, faint band on the horizon, but a void isn't a perfect vacuum. It's not truly empty. It has a thin, diffuse mist of hydrogen gas. And the invisible scaffolding of dark matter, just in much lower concentrations. Its formation is the direct counterpart to the growth of the walls and clusters. Those primordial ripples, The regions that were slightly underdense had less gravity, so over the eons, gravity pulled matter away from these underdense regions. Toward the overdense ones, the voids were drained. There the basins left behind as the landscape eroded into hills and mountains, and this is still happening. Voids are actively growing. As the filaments pull matter in, the voids expand outward. Their boundaries get sharper. Their geometry isn't passive. The spherical pressure of an expanding void actually helps mold and compress the filaments around it. Like dough rising between the spaces of a basket, they're dynamic actors. Their emptiness actively shapes the fullness elsewhere, so the Sloan Great Wall doesn't exist alone. It's one side of a coin, the other side is a void or a network of voids on a comparable scale. The universe is a balance, presence and absence, the immensely crowded and the unimaginably empty. This cosmic web is the visible testament to that balance, but what if the web is just a shadow, a trace of something far stranger, woven into the fabric of space itself? That entire landscape, the web of light and the voids, it's shaped by something we can't see. To understand the largest structures, you have to meet the primary architect. A substance that makes up about 85% of all matter. We call it dark matter. It's the invisible hand that sculpted everything. Think of it like a building's frame. You see the walls, the glass, but the strength, the shape, the existence of the structure depends on the steel skeleton inside. Dark matter is that cosmic skeleton. It doesn't emit light, it doesn't absorb or reflect it. It's utterly dark to every telescope. We only know it's there because of gravity. We see its pull on galaxies. Bending light, governing the motion of stars, its gravity is the glue that holds the universe together on the grandest scales. Here's how it worked. After the Big Bang, the universe was a nearly smooth soup. But there were tiny ripples in density. Now, ordinary matter, the protons, the gas that would become stars, it feels pressure, it pushes back, it resists clumping. Dark matter is different. It doesn't interact with light. It doesn't interact with itself except through gravity. It feels no pressure. So as the universe expanded, those tiny ripples were a playground. Dark matter could start to clump together immediately, unimpeded. It began to collapse under its own gravity first. Over hundreds of millions of years, these clumps grew. They merged, they drew in more. They created a vast, invisible network of gravitational valleys and hills. This was the cosmic scaffolding. The frame was built in the dark. Then the normal matter, the gas, it simply flowed into these pre-existing wells. Like water following the contours of a landscape, the gas pooled at the deepest points. It cooled. Eventually it ignited into the first stars and galaxies. Those galaxies didn't form randomly. They lit up at the intersections, along the filaments of this invisible dark matter web. We are just the luminous decoration on a hidden framework. We can see this process in simulations. Projects like the Millennium run. They don't just simulate stars. They start with the theoretical seeds of dark matter. They let the laws of physics play out over billions of virtual years. The result is a cosmic web. A vast, interconnected network of dark matter filaments with dense clusters at the nodes. When astronomers overlay the positions of real galaxies onto these simulations, they match almost perfectly. The model built on dark matter predicts the reality we see. Without this unseen substance, the universe would look different. Gravity from visible matter alone is far too weak. It could never have gathered material fast enough across such vast distances to build the great walls and superclusters in the time the universe has existed. The cosmic web would have never formed. There would be no grand architecture, just a sparse, drifting haze of gas and stars. Dark matter provided the gravitational pull. The deep wells, the cosmic blueprint. It is the silent, dominant force that arranged the universe into this structured tapestry we are only beginning to map. And if dark matter built the stage, what strange actors might it have allowed to perform upon it? The cosmic web started with a whisper, a quantum whisper. To find the origin of the Great Walls, you have to go back to the very first instant, a fraction of a second after the beginning. That's the epoch of cosmic inflation. The universe in that instant underwent a growth spurt, an exponential expansion from smaller than a proton to something macroscopic, less than a blink. This wasn't the slow expansion we see now. This was a violent stretching of space itself, and during that event something happened. The quantum world is never perfectly still. It's a sea of tiny fluctuations. At that level, empty space isn't empty. It fizzes, particles pop in and out. These are quantum fluctuations. In that primordial, inflating universe, these microscopic ripples were caught. And as space stretched, those tiny ripples were stretched with it. They were blown up from the quantum scale to the cosmic scale. Think of a tiny wrinkle on a deflated balloon. Inflate the balloon to the size of a city. That wrinkle becomes a massive crease. That's what inflation did. It took quantum fuzz and imprinted it across the entire sky. Those stretched ripples were variations in density. Some regions of the newborn universe were slightly denser. The difference was minuscule, 1 part in 100,000. But in a universe with gravity, that was enough. Gravity is an amplifier. It loves density. Over billions of years, gravity began its work. It pulled a little more matter toward those denser spots. As more matter gathered, the gravity grew stronger, which pulled in even more matter. A snowball effect on a cosmic scale. Those initial overdensities became the seeds. The blueprints for every galaxy cluster, every filament, every great wall. The entire architecture of the cosmic web was encoded in those first quantum whispers. And we have a picture of this moment, a baby picture of the universe. It's called the cosmic microwave background, the afterglow of the Big Bang, released when the universe was only 380,000 years old. Before stars or galaxies, just a hot, glowing fog. That light has been traveling for over 13 billion years, and when we map its temperature, we see a pattern. A mottled map of tiny hot and cold spots. Those spots are the direct imprint of those primordial ripples, the seeds. The cold spots are where matter was slightly denser. Having already done a little work to pull energy out of the light, that pattern on the microwave background is the universe's genetic code. It contains the instructions for everything that would grow. The largest structures have the smallest origin, a quantum flicker, frozen into the sky and grown to impossible size by gravity and time. The universe isn't just that dark skeleton. What we actually see glowing is something different, baryonic matter, protons, neutrons, electrons, the stuff of stars and planets, the ordinary matter. The kind that light touches. Once the dark matter structure was there, this normal gas started to move. It followed those gravitational streams, collecting in the dark matter halos in their deepest parts. Think of a mist filling the crevices of a sculpture. The sculpture is dark matter. The mist is the gas waiting to shine. Inside these halos, the gas needed to cool. To collapse, it lost its heat, it radiated it away, and as it cooled, it got denser. It began to spin, forming clouds, and inside those clouds, under all that pressure, the first stars were born. That was a revolution. They weren't like our sun. They were monsters, hundreds of times heavier. They burned fast and died young, in supernovas after just a few million years. Those first galaxies were small and chaotic, but they were the seeds for everything we see in the web now. But this story isn't only about gravity pulling things together. There's a force pushing back, feedback. The universe has its own controls. When those first massive stars died, they exploded. A supernova is one of the most powerful events there is. It shocks the nearby gas, heats it to unbelievable temperatures. It can even push that gas right out of the galaxy, back into the space between galaxies. It's like a fire clearing out a forest. It stops new stars from forming for a while by taking away the fuel. It's a cycle, a self-regulating one, and there's an even more extreme kind of feedback. In the center of many galaxies, ours too, there's a supermassive black hole. When gas falls toward it, it doesn't just disappear. It forms a disk, a swirling, incredibly hot disk. That creates an active nucleus, a source of intense radiation and jets that can stretch for thousands of light years. These jets can heat the gas across a whole cluster of galaxies, stopping it from cooling and making new stars. They're like cosmic blowtorches, sculpting the biggest structures from the inside. So how a galaxy looks, or a cluster, isn't just about the gravity of its dark matter halo. It's about a struggle, a back and forth. Gravity pulls gas in to make stars, then stellar explosions and black holes push that gas back out. This dance between making and breaking decides how bright a galaxy is, how many stars it forms, what shape it takes. It's why some galaxies in the dense knots of the web are old and red, their star-making stopped by fierce feedback. And others in the quieter strands are still blue, still giving birth. The glowing pattern of the cosmic web isn't a fixed picture, it's changing, always. Painted by the pull of what we can't see and the fierce energy of what we can. The whole cosmic structure, from dwarf galaxies to superclusters, came from one force. Gravity. It builds from the bottom up. That's hierarchical structure formation. The universe builds its largest things through mergers and acquisitions across all of cosmic time. It's a construction project, but the smallest bricks come first. It started with dark matter. Those early ripples made tiny halos, just specks of gravitational influence. Gravity pulled them together. They collided, merged, coalesced into larger halos. That was the first phase, happening in the dark. Then the ordinary matter, the gas, could flow. Drawn into the gravity wells of those dark halos, the gas cooled, condensed, and ignited. The first luminous objects were born, proto-galaxies, like villages. And villages grow into towns, into cities. These proto-galaxies were destined to merge. Gravity orchestrated a slow dance of collisions. Two small galaxies would spiral together over hundreds of millions of years. Their stars mingling, their gas clouds crashing, triggering bursts of new stars. The result was a larger galaxy. This repeated over and over. Streams of gas and smaller galaxies flowed along dark matter filaments, feeding the growth at the intersections. It's like streams forming creeks, creeks feeding rivers, rivers pouring into basins. The cosmic web is that river system. Gravity is the current. This bottom-up construction didn't stop at galaxies. Gravity kept working. Individual galaxies gathered into small groups. Our Milky Way is in one, the local group, with Andromeda and dozens of smaller galaxies. And these groups are moving. Drawn by the gravity of larger structures, they flow along the web toward dense nodes. Where many groups converge, you get a galaxy cluster, a metropolis of thousands of galaxies, like the Coma cluster. And clusters are the building blocks for the largest bound structures, the superclusters. Superclusters are so vast they aren't permanently bound, but they're the final gathering in this chain. The crucial point is this process isn't over, it's ongoing right now. The evidence is in our own neighborhood. The Milky Way and Andromeda are on a collision course. In about 4 billion years, they'll begin a slow merger. They'll dance, twist, coalesce into one giant elliptical galaxy. We are living proof. We are participants in the hierarchical construction. From the first quantum whisper to the Great Walls, gravity's patient pull has woven the cosmic web. It spent 13.8 billion years assembling grandeur from tiny seeds, one merger at a time. And looking at this structured immensity, a new question comes up. What if some of these structures are so vast they shouldn't exist at all? Gravity built all this. But how can we be sure? You can't run the universe twice. You can't change its rules and see what happens. Not in reality. but you can in a machine, so that's what we did. We built a simulation of the entire universe, a virtual cosmos, from the equations of physics to a digital echo of everything. It's not an animation. It's a monumental calculation. You start with the known laws, the pull of gravity, the flow of gases, the push of dark energy. You turn these forces into billions of lines of code. Then you feed that code into the most powerful supercomputers, machines that do quadrillions of calculations every second. Their job is to solve an impossible puzzle. Starting an instant after the Big Bang, projects like IllustrisTNG do this. They define a box of virtual space, hundreds of millions of light years across. They fill it with a digital soup, dark matter and gas, seeded with those tiny quantum ripples. They press start and they let it run. For months, the supercomputer calculates the interactions of trillions of particles. It watches gravity work over virtual billions of years. It models gas collapsing into the first stars, the feedback from supernova, the appetite of supermassive black holes. A universe in a box growing up. The results are clear. When the simulation finishes, scientists look inside. They make a three-dimensional map, and what they see is unmistakable. A vast cosmic web, filaments of galaxies twisting through space, dense clusters at the intersections, immense spherical voids. The virtual universe looks almost identical to the maps from our telescopes. The simulated structures match the observed ones, in scale, in shape, in distribution. It's a profound validation. It tells us our understanding is essentially correct. The basic ingredients, dark matter, gravity, the initial conditions, they're right. The skeleton we predicted is the one we see, but these simulations are more than a test. They're a time machine, a laboratory. You can rewind and watch, step by step, how a specific Great Wall assembled. You can trace a galaxy cluster back to its first dark matter halo. You can also experiment. What if dark matter behaved differently? What if gravity changed on large scales? Alter the rules in the code. Rerun the simulation. See what kind of universe results. If it doesn't look like ours, you rule that physics out. This virtual lab lets us explore questions we could never ask of the real cosmos. It turns speculation into a science of what-ifs. The bridge between our theories and the observed universe is built of silicon and light, a digital twin helping us decipher the true story. And as these simulations get more detailed, they reveal something unsettling. Some of the structures we see out there might be too big for our story to explain. These digital twins help us find our place. We're not in a random void. We're part of a specific, immense structure. Our galactic home has an address. It's called the Laniakea Supercluster. That name came out in 2014. It's from Hawaiian. It means immense heaven, and that's a perfect description. Laniakea is our local neighborhood in the cosmic web. But it's a neighborhood on a scale that's hard to think about. It holds about 100,000 galaxies. Our Milky Way is one of them. Andromeda is another. The Virgo cluster, with over 1,000 galaxies, sits near its heart. All of that is part of Laniakea. But a supercluster isn't a single bound object, not like a galaxy cluster. You can't point a telescope and see its edge. It's more like a river basin, a gravitational watershed. Picture a vast landscape of hills and valleys. When rain falls, every drop follows gravity, trickling into streams, then rivers, all flowing toward the lowest point. Laniakea works that way. It's defined by motion. Every galaxy inside it, ours included, is flowing, drifting along the invisible contours of the cosmic web, all moving toward a common center of mass. Astronomers call that focal point the Great Attractor. That motion is the key. By mapping the velocities of tens of thousands of galaxies, scientists traced these cosmic currents. They saw our entire local group, the Virgo cluster, countless other groups, all part of one grand, slow river, flowing toward a mysterious, hidden mass. The Great Attractor itself is hidden behind the dense plane of our own Milky Way, but its pull is undeniable. It's the heart of our immense heaven. The scale is hard to grasp. Laniakea spans about 520 million light-years. If you stood at one edge, the light from the other side started its journey before complex life existed on Earth. And we are inside this flow. Right now, our galaxy is moving toward the Great Attractor at over 600 kilometers every second. We're passengers on a journey that will last for many billions of years. This redefines home. Earth is a planet in the solar system. The solar system is in the Milky Way. The Milky Way is in the local group, and the local group is a single droplet in the vast river of Laniakea. It shows the cosmic web isn't a static painting. It's a dynamic, living map, a chart of motions and flows that are actively shaping the universe's future, even now. And if our entire supercluster is flowing toward one hidden point, it makes you wonder what other, even larger currents might be moving out there in the darkness beyond. The Great Attractor is a gravitational anomaly. It's a huge concentration of mass pulling on thousands of galaxies, ours included. It's in the direction of Centaurus and Norma. But we can't see it. The center is hidden behind the disk of the Milky Way. It's like a city behind a permanent fog. You know it's there because everything is moving toward it. We measure that pull, we map the motion, but the source itself is still hidden. What we can see around the edges are big galaxy clusters, like the Norma cluster. They add to the gravity. The Great Attractor isn't one object. It's probably the core of our supercluster where filaments of the cosmic web meet. It's the deepest valley nearby. And everything is sliding down into it, but gravity isn't just a pull. It's also an absence of push. For every hill, there's a valley, and for our motion, it's not just a pull from one side. There's also a push from the other side. Opposite the Great Attractor, there's a huge cosmic void, the dipole repeller. The attractor pulls us in, and the repeller, in a way, pushes us away. How can emptiness push? A region that's very underdense has much less gravitational pull than average. So while the dense attractor tugs us, this vast void doesn't hold us back. It creates an imbalance. From here, it feels like we're being pushed away from the emptiness because we're not being pulled toward it equally. It's the shadow to the attractor's light. The dipole repeller is a spherical void, hundreds of millions of light years across, so empty that its lack of gravity is itself a force. Our galaxy's journey isn't a simple fall. It's a complex drift, surfing cosmic currents. The combined landscape, the hills of superclusters and the valleys of voids sets our motion. We're flowing from the region of least resistance, the repeller, toward the region of greatest attraction. This shows the universe isn't a static stage. It's a dynamic, undulating fabric. The force shaping the largest structures isn't a mystery. It's the simple, relentless geometry of gravity. Matter warps space-time, creating slopes, and everything from a single galaxy to a whole supercluster rolls downhill. We're riding a river that's been flowing for billions of years, carried by the silent topography of the cosmos. And if our local flow is shaped by features this large, what do we see when we map the motion of the entire observable universe? The local flow is part of a larger current. To find the largest structures, you have to look far away, which means looking back in time. Back in 2013, astronomers announced something. They called it the HERCULES-CORONA BOREALIS Great Wall. It's the largest single structure we've ever identified, and they found it by looking at explosions. Gamma-ray bursts, these are the most powerful explosions since the Big Bang. They happen when the most massive stars die catastrophically, or when ultra-dense objects like neutron stars collide. For a few seconds, they outshine entire galaxies, and because they're so bright, we can see them from incredibly far away. From the early universe, the team used data from space telescopes to map where these bursts were. Their reasoning was these bursts come from massive stars, so they should show where galaxies were concentrated. They're like temporary beacons, and when they plotted the positions, they saw a pattern. A huge concentration, a wall of beacons across a region of sky in Hercules and Corona Borealis. The size is hard to grasp, about 10 billion light-years across. The observable universe is about 93 billion light-years across, so this one structure would span roughly a tenth of it. That scale is the problem. It challenges a foundational idea, the cosmological principle, which says that on the largest scales, the universe is homogeneous. It should look roughly the same everywhere, with no single structure dominating. A wall 10 billion light-years long seems to violate that. It would be a feature so large it defines the cosmos. The question is it real? The debate is intense. The challenge is we're seeing it in two dimensions, and we're using gamma-ray bursts as proxies. Are we seeing one continuous filament of the cosmic web, woven across an impossible distance? Or is it a chance alignment, a line of sight overlap of several smaller, unrelated filaments? It's like seeing several mountain ranges lined up and mistaking them for one chain. The data is sparse, the beacons are rare, the statistics are complex. Some studies support it, others say it could be a fluke, an artifact of how we map such distant epochs. This controversy isn't a failure, it's science at the edge. It shows what happens when discoveries bump against fundamental principles. Either we've found a structure that forces us to rethink homogeneity, or we're being fooled by the shadows. Pushing our techniques to the limit, the Hercules-Corona Borealis Great Wall, whether a true titan or a mirage, is a frontier, a question mark written across the sky. It reminds us our map of the universe is still being drawn, and its largest features may still surprise us. That potential wall, 10 billion light-years long, points to a deeper tension. It makes us question a bedrock assumption in our cosmic model, the cosmological principle, and that's not just a technical term. It's a philosophical stance baked right into the equations. It states two things. First, isotropy. The universe looks the same in every direction we look. And second, homogeneity. On the largest scales, the universe is smooth. It has no center, no edge, no single special place. Matter and energy are spread evenly when you zoom out far enough. This principle is why the Big Bang theory works. It lets us treat the universe as a single, evolving entity with known rules. Without it, our physics would be a local curiosity, not a universal truth. So when we find a structure that seems to stretch across a significant fraction of the observable universe, it directly asks, is the cosmos truly smooth? Does a filament of galaxies 10 billion light-years long count as a large scale, or is it just a particularly thick thread in an otherwise uniform tapestry? This is where cosmology meets semantics. How big is big enough? Proponents of the principle argue that even these colossal walls are part of the expected spectrum. The cosmic web has filaments of all sizes. Finding an exceptionally long one in a survey covering billions of light-years isn't a violation. It's a statistical possibility. A rare but natural peak in the density fluctuations planted by inflation. In their view, if we could step back far enough, far beyond our observable horizon, we would see an endless, foamy sea of such structures with no single one dominating the whole. Skeptics, though, see a crack in the foundation. They point out the theoretical limit for a structure's size, based on those primordial ripples, is around 1.2 billion light-years. The Hercules-Corona Borealis Great Wall, if real, is nearly 10 times that. It wouldn't be a thread in the tapestry. It would be a dominant seam, warping the fabric of space-time on a fundamental level. Its sheer scale suggests the early universe's fluctuations might have been more dramatic, or that some unknown process later amplified them beyond our current understanding. The resolution may not be in discarding the principle, but in refining what we mean by large scale. perhaps our observable universe isn't large enough to see true homogeneity. We're inside a single bubble, and this great wall is just one feature of our local bubble's interior. True smoothness might only appear on scales far larger than we can ever see. This debate pushes cosmologists to sharpen their tools and definitions. They run larger simulations, take deeper surveys, and develop new statistical tests to measure the universe's lumpiness. The goal is to find the transition scale, the precise zoom level where the intricate web finally blends into a smooth, uniform haze. Whether the Great Wall is a true titan or a trick of perspective, its very possibility reminds us our cosmic maps are still provisional. The final word on the universe's architecture is yet to be written. The cosmic web has a rhythm, a pattern that repeats. It's a fossil from the universe's earliest moments called Baryon acoustic oscillations. To see it, you have to go back before anything existed, before stars, before galaxies. The universe was just a hot, dense fog, a plasma of particles and light all mixed together. In that state, matter and light were locked together. The light photons pushed outward with tremendous pressure, but gravity from all that matter pulled inward. That conflict set everything in motion. It made the universe ring. These forces created sound waves, real pressure waves moving through the cosmic fluid. They weren't sound you could hear, but waves of density, regions of higher and lower pressure expanding outward from every initial lump, like ripples from a stone in a pond. For hundreds of thousands of years, these waves raced through the plasma. The photons tied to the matter drove them outward. Then, a change. The universe cooled enough for electrons and protons to combine. They formed neutral hydrogen atoms. The fog cleared instantly. The photons were suddenly freed, streaming away in all directions. We see that released light now as the cosmic microwave background. But for the matter, something else happened. With the photons gone, the pressure wave just stopped. It froze. The ripples in the density of matter were imprinted, like a wave frozen in ice. That left a specific scale in the universe's structure. The distance those sound waves traveled before freezing, about 500 million light-years. It became a preferred spacing. Imagine dropping millions of pebbles into a pond at the same time. The ripples expand and interfere. If the pond instantly froze, you'd see a pattern. A clear, repeating distance between the rings. That's what happened to the cosmos. Later, when galaxies began to form, they were more likely to form at the crests of these frozen waves. So now, if you survey a huge volume of galaxies and measure the distances between them, you find a signal. A slight excess of galaxy pairs separated by about 500 million light-years. It's not a wall you can see. It's a statistical echo, a fossilized ripple. For cosmologists, it's a gift. It acts as a standard ruler etched into the sky. We know its true physical size from the physics of the early universe, so we can use it to measure how the universe has stretched over time. By looking at galaxy surveys from different eras, we see how this ruler appears to us. If expansion had been constant, the ruler would look a certain size, but measurements show it appears larger at greater distances. That means expansion has been accelerating. This Boötes signal confirms dark energy independently. It links the vibrations of the newborn universe to the force shaping its fate. The largest structures hold the story of gravity's pull and the fading echo of the cosmos's first sound. That faint afterglow from the Big Bang, it's more than just a baby picture. It's a backlight, a cosmic screen shining through everything that formed after. And when something massive passes in front, it leaves a shadow, not a dark shadow, but a specific kind of imprint. That's the Sunyaev-Zeldovich Effect. It's one of our most powerful tools for mapping the universe's hidden giants. So you have the cosmic microwave background, this uniform, ancient light coming from everywhere. Now imagine that light has to travel through a massive galaxy cluster to reach us. That cluster isn't empty. It's filled with an incredibly hot gas, a plasma of electrons and ions, so hot it glows in X-rays. As the CMB photons pass through that superheated fog, they don't just go through, they interact. The high-energy electrons in the gas give those passing photons a tiny kick. They scatter them, boosting their energy just a little, and that scattering leaves a cold spot in the CMB's temperature, right at the cluster's location. It's a subtle distortion, a fingerprint in the microwave light. What's amazing is, this effect doesn't care about distance. Whether a cluster is nearby or at the edge of the observable universe, the size of this imprint on the CMB is roughly the same. It doesn't fade with redshift. That makes it a perfect ruler for finding the most massive structures across the entire history of the cosmos. To catch this whisper-thin signal, astronomers build telescopes in extreme places. The high, dry Atacama Desert in Chile, the frigid plateau at the South Pole, these locations have incredibly stable, transparent atmospheres, perfect for staring at the microwave sky with exquisite sensitivity. Telescopes like the Atacama Cosmology Telescope and the South Pole Telescope scan the heavens not for stars, but for these specific cold spots in the CMB. Each spot reveals a massive galaxy cluster, a knot in the cosmic web, often so distant its light is too faint to see directly. By cataloging thousands of these clusters across cosmic time, these surveys do more than make a map. They trace the growth of structure itself. They show how the number of massive clusters has increased over billions of years. That growth rate is a direct test of our cosmic models. It tells us the density of matter in the universe, and crucially, it measures the strength of dark energy, which works against gravity's pull to slow down the formation of these titans. So by reading the shadows cast on the universe's first light, we're decoding the forces that shaped everything after. We're just seeing the first hints of this structure, these faint traces. But that's about to change. A whole new set of observatories is coming online, and they're going to map the universe in a way it's like moving from a rough drawing to a photograph. An extremely detailed photograph. There's the Vera C Rubin Observatory. It's built on a mountain in Chile, and it's about to start something called the Legacy Survey of Space and Time. This is a 10-year project. It will scan the entire southern sky every few nights. The camera is enormous, the size of a small car. It will capture so much light, so much sky. It's going to catalog tens of billions of galaxies. That number, it's more galaxies than there are people on Earth, and it won't be a single picture, it'll be a movie. A decade-long movie showing galaxies moving, changing, showing how the cosmic web itself flows and shifts. It will find billions of those distant galaxies, the ones whose light gets stretched and bent by dark matter's gravity. That bending, it lets us map the invisible structure. It will give us the most precise map of that dark skeleton we've ever had. Then there's Euclid. That's a space telescope launched by Europe. It's built for this, to study the dark universe. It will measure the shapes and positions of over 1 billion galaxies. Across a huge portion of the sky, its focus is on a subtle effect: weak gravitational lensing, the tiny distortions in galaxy shapes caused by dark matter bending light. That data, it will let us trace the web in 3 dimensions, and not just now but back over 10 billion years. We'll see how the filaments grew thicker, how the voids expanded, all under the push and pull of dark matter and dark energy. And looking further out, there's the Nancy Grace Roman Space Telescope. Its field of view is massive, 100 times wider than Hubble's. It will do these vast, deep surveys. It will find thousands of new galaxy clusters. It will map matter distribution with such fine detail we might see new types of structures, features in the cosmic web that our current maps are just too blurry to show. The data from all this, it will be a flood. We're moving from studying thousands of galaxies to billions of them. It's the difference between mapping a coastline and mapping a whole continent. And with these new maps, these exquisitely detailed charts, we will test our theories with a kind of brutal precision. We'll see if the patterns from our simulations match. The distribution of voids, the thickness of filaments, the clustering of galaxies, does it match reality perfectly? Or are there wrinkles? Those wrinkles, they could be the clue. They might tell us what dark matter actually is. Cold, warm, something else entirely. They could show us if dark energy has changed over time, or if our understanding of gravity, if it needs revision on the largest scales. This next decade, it will change the cosmic web from a model, a fascinating idea, into a measured reality, a living structure. It will bring us face to face with the fundamental forces. The ones that wove the universe into this tapestry, this grand tapestry we're only just starting to see. There's a basic expectation in cosmology that there should be a limit to how big any structure can get. A distant scale where the universe stops being lumpy and becomes smooth, that's the homogeneity scale. Our models put it somewhere around 300 to 400 million light-years. Beyond that, no single feature should stand out, but the walls we're finding don't just cross that line, they ignore it. The Sloan Great Wall is over 1 billion light-years long. The HERCULES-CORONA BOREALIS candidate is even larger by an order of magnitude. So the question is, what's going on? Are these just rare exceptions, or do they mean something's missing in our understanding? One idea goes back to the very beginning, to inflation. In the standard picture, the quantum ripples from inflation follow a bell curve. Most seeds were small. A few were medium. Extremely large ones were supposed to be incredibly rare, but some theories suggest the distribution might not have been a perfect bell curve. It could have been non-Gaussian, which is a technical way of saying there might have been a few dramatic outlier ripples, super large seeds, and if one of those was in the right place, gravity could have spent 13.8 billion years growing it into something enormous. A cosmic jackpot, a wall of staggering size. There's another possibility. It's more unsettling because it questions our tools, not our theories. When we look at the farthest edges of the observable universe, we use redshift to measure distance. But at those extremes, the relationship between redshift and true distance depends entirely on our model of cosmic expansion, on how dark energy behaves over time. If that model is even slightly off, our distance calculations could be skewed. What looks like a single, continuous wall 10 billion light-years long might actually be a chance alignment. Several smaller, unrelated filaments stacked along our line of sight, a cosmic mirage, a trick of perspective, amplified by the vastness of space and the limits of our current data. This question sits right at the frontier of cosmology. It's a tension between what we see and what we predict. These great walls aren't just landmarks. They're stress tests for our entire picture of the cosmos. They force us to sharpen our simulations, to design deeper surveys, to question comfortable assumptions. Our current catalogue of giants is provisional. It's a first draft written with the data we have. The next generation of telescopes will map billions of galaxies. They'll give us the definitive answer. They'll either show these colossal walls as rare but natural peaks in a grand, homogeneous tapestry, or they'll reveal a universe that's fundamentally lumpier. More textured, more surprising than we ever imagined. The search for the largest structure is really a search for the limits of our own understanding. Gravity spent billions of years building the cosmic web, but there was another force working against it. Dark energy. It's what makes the universe expand faster. For most of history, gravity was in charge. It pulled matter together, fighting the expansion. It was a close fight, and gravity was winning. It gathered gas into galaxies, galaxies into those giant filaments. Then, about 5 billion years ago, things changed. The universe had grown, matter had spread out. Dark energy's influence stayed the same, or maybe even got stronger. It passed a point. Dark energy became the main force, and the time of building large-scale structure that ended. the future dark energy writes, is one of isolation. Locally, gravity's hold is permanent. The Milky Way and Andromeda will merge. The local group becomes one big galaxy. Clusters like Coma are so tightly bound, their galaxies will orbit forever, separate from the expansion outside. They become islands, but the space between the islands, that's where dark energy rules. The accelerating expansion will stretch the cosmic web itself. Like a drawing on rubber pulled from all sides, the filaments, the threads between the nodes, they'll get thinner. They'll start to snap. Over timescales much longer than the universe's current age, the effects get deep. Any galaxy not already in a group or cluster gets carried away by space itself, rushing outward. They recede faster, their light stretches, reddens until they fade from view completely. They pass beyond what we could ever see. For any astronomers later on, in that merged local group galaxy, the universe would look totally different. The night sky, once it had the glow of distant walls and superclusters, goes dark. The cosmic web dissolves. All that's left are the lights of their own island, drifting in an endless, expanding black. That's the final chapter for cosmic structure. Dark energy sets the fate for the very architecture it helped show us. It's a quiet, relentless force. It means the universe's largest creations aren't forever. They're magnificent but temporary, a grand tapestry woven in the early light, only to be slowly undone by the dark. The cosmic web fits our current model of the universe. But the model itself might be incomplete. The standard framework is lambda cold dark matter, lambda CDM. It's an elegant story, a universe from a hot Big Bang. Structure built by dark matter's gravity, its fate now driven by dark energy, that lambda. It's been successful. It predicted the pattern in the cosmic microwave background. It explains how galaxies rotate. The simulations it produces look just like our sky. But then you have these structures, the Great Walls. They push the theoretical size limit. And that creates a tension, a low hum. When observations nudge against a model's predictions, that's not a failure. It's the engine. It forces the question. Are there other ways to explain the universe's architecture? One alternative questions the need for dark matter entirely, modified Newtonian dynamics. And the idea is simple, radical. What if our understanding of gravity is subtly wrong on the scale of galaxies, instead of an invisible substance? In MUND, gravity behaves differently when its pull becomes extremely weak. Like in the outskirts of galaxies, that tweak can explain why stars in galactic halos orbit so fast. The very observation that led to dark matter. Proponents have explored whether a relativistic version of MUND could also build a cosmic web. Some simulations suggest it might. It might produce filaments, but the challenge is immense. MUND must also explain the bullet cluster, where the mass of colliding galaxy clusters is separated from the visible galaxies. Mapped by gravitational lensing, that result points to some form of dark, collisionless matter. It must account for the precise peaks in the cosmic microwave background. So far, lambda CDM does this with one coherent set of rules. MUND remains a compelling challenger, unproven. It shows how extreme data pushes us to question fundamental laws. Other ideas look not to gravity's laws but to the universe's earliest moments, exotic defects in the fabric of space-time, left over from the phase transitions of the hot Big Bang. Cosmic strings, theoretical, infinitely thin lines of immense density, thinner than an atom but with the mass of a mountain range per inch. They could have acted as gravitational scaffolding, attracting matter along their length, seeding the first filaments, domain walls, two-dimensional sheets of energy. They could have carved the universe into vast, distinct regions. These relics are hypothetical, but if they existed, they could have planted seeds for superstructures, larger than inflation's quantum ripples alone would allow. A different kind of blueprint, etched by topological knots in reality itself. None of these alternatives have displaced the standard model. Lambda CDM remains the most complete framework we have. Predictive, but that's why the Great Walls matter. They are not just landmarks, they are stress tests. They are the anomalies that keep cosmology honest. Vibrant, open, a theory that faces no challenges becomes dogma. The constant tension between what we predict and what we find in the deep sky. It ensures our map of the universe is always being redrawn. Always inviting a deeper story. The search for the largest structures is a search for the limits of our own understanding, and perhaps a glimpse of the physics that lies just beyond it. These immense structures, they're not just distant abstractions. Their story is our story. Every atom in your body, every element heavier than hydrogen and helium was forged inside a star. That star, our sun, it was born from a cloud of gas, and that cloud was part of a grander cycle, a cycle orchestrated by the cosmic web. The same gravitational forces that sculpted the Sloan Great Wall, they also nudged a local filament of gas to collapse. It formed the spiral arm of the Milky Way, where our solar system would later coalesce. We are not separate from this architecture, we are a product of it. Studying these largest structures is, in the most literal sense, an investigation into our own cosmic ancestry. It traces the chain from the first quantum ripples to the planet beneath our feet. Philosophically, this knowledge redefines our place. For millennia, we looked up and saw a celestial sphere, a dome of light centered on our world. Then we learned Earth orbited the sun. Then we learned the sun was one star among billions in a galaxy. And now we see that galaxy as one tiny speck, a drift in a river of galaxies flowing through an immense supercluster, which is itself just one thread in a web spanning the observable universe. This is a profound humility, a necessary one. We inhabit a quiet suburb in an island city, within a continent of light, in a cosmos whose full geography we may never fully know. The scale doesn't diminish us, it contextualizes us. We are the part of the universe that has become conscious, able to look back and trace the lines of its own construction. This pursuit also fuels tangible progress here on Earth. The drive to map the cosmic web pushes technology to its limits. It demands cameras with billions of pixels, telescopes in space and in extreme environments, supercomputers that perform calculations once thought impossible. The algorithms developed to find faint galaxies or untangle gravitational lensing. They find applications in medicine, data science, artificial intelligence. The quest to understand the universe's largest things constantly refines our tools for understanding our own world. Ultimately, this exploration answers a deep human need. The need for context. We are storytellers by nature. We look at the scattering of stars and we ask, what does it mean? How does it fit together? Modern cosmology provides that narrative. It transforms the night sky from a random, beautiful glitter into a historical document. Each point of light is placed within a timeline, within a structure, within a dynamic, evolving saga that began nearly 14 billion years ago. We are small within it, yes, but we are also the readers of that story. We are the universe becoming aware of its own shape, its own history, its own breathtaking scale. In mapping the Great Walls, we are not just charting distant geography. We are finding our address in existence. You can see this fractal organization right here in our own galactic neighborhood. Just past the edge of Laniakea, there's a huge structure called the Pisces-Cetus Supercluster complex. If Laniakea is a city, then this complex is the whole metropolitan area. It connects several of these cosmic cities together. It's not one bound object, it's a network, a web inside the web. It holds Laniakea, the Perseus-Pisces supercluster, and other massive galaxy gatherings. Together, they might form one single filament in the cosmic web, a thread nearly 1 billion light-years long. Mapping this region has been a lesson in cosmic connection. Astronomers spent decades charting galaxy positions and velocities here, tracing the flows. They showed how the Great Walls and filaments intersect and branch. You can see how Laniakea's river of galaxies links to other flows. The borders between superclusters aren't sharp. They're zones of interaction where one giant's gravity slowly yields to the next. It's like mapping a continent's watersheds, seeing how every stream feeds a larger basin. This complex is a perfect real-world lab. It's relatively close, so we see it clearly. We can measure the precise motions of galaxy groups within it, watching them stream along the filamentary highways. Then we compare that observed flow directly to supercomputer simulations. Does the virtual universe built from lambda CDM produce a structure that looks and acts like Pisces-Cetus? So far, the answer is yes. The simulations reproduce the connectivity, the branching patterns, the overall dynamics. That close match gives us powerful, localized validation for our models of how gravity built the universe. This case study shows the fractal nature of cosmic structure. Zoom in, you see a galaxy group, a collection of islands. Zoom out, that group is a single point in a galaxy cluster, a city of islands. Zoom out further, that cluster is part of a supercluster, a nation. And now we see superclusters themselves are nodes in these vast, continent-sized complexes. The same pattern repeats at every scale, dense nodes connected by filaments. From the smallest bound groups to the largest observable filaments, the same physical principle is working. Gravity's patient, bottom-up assembly, acting on the primordial blueprint. The Pisces-Cetus supercluster complex shows us the universe isn't just structured, it's deeply, hierarchically interconnected. Our home supercluster isn't an isolated island. It's a neighborhood in a cosmic megalopolis, one thread in a tapestry whose full pattern we're only starting to trace. The cosmic web, the filaments aren't just galaxies. They're outlined by galaxies, traced by them, but the real substance is more diffuse. You have to look between the bright points, at the highways themselves. That's the intergalactic medium, the IM. It's a superheated gas, ghostly, filling those vast expanses, a fog of primordial hydrogen and helium, so thin, the best vacuum we can make on Earth is dense by comparison. In some places, maybe 1 atom per cubic meter, and yet that's where most of the normal matter in the universe actually is. It's the ocean. Galaxies are just islands in it. We know it's there because of the light. Quasars give us a window. Their brilliant light beams across billions of light years, and as it travels, it passes through this gas. Atoms in the gas absorb specific wavelengths. So when astronomers take that light and spread it into a spectrum, they see a forest of dark lines, the Lyman alpha forest. Each line is a shadow, a record of a single cloud of hydrogen the light passed through. The pattern is complex. A dense thicket of lines means the light went through a crowded filament. A sparse set means it traveled through a void. That forest is like a barcode, a readout of the density and temperature along that exact line of sight. Study thousands of those spectra, and you can map the distribution statistically in 3 dimensions. It's like a tomography scan of the universe's skeleton. This gas is the main reservoir of baryonic matter, the ordinary stuff. It's the raw fuel. Galaxies form from it. They keep feeding from it. A galaxy's story is pulling this gas in, cooling it, making stars. But the IGM isn't passive. Its state tells us about the forces shaping everything. Its distribution traces the gravitational landscape, the one sculpted by dark matter. The gas pools in the same filaments and knots. It lights up the dark matter scaffold, like a neon sign tracing a wire, and its temperature is a record. The IGM is hot, millions of degrees. That heat doesn't come from stars inside it, there aren't any. It comes from the galaxies embedded in the web. When the first massive stars exploded, they blasted energy out. Later, radiation and jets from supermassive black holes pumped more heat in. That process is called feedback. It heats the gas, stirs it, prevents it from cooling too fast, regulates how fast galaxies can grow. So the temperature today is a fossil record of that billion-year energy exchange, a testament to the universe's fierce youth. Understanding this medium completes the cosmic matter census. For decades, a portion of normal matter was missing. The predicted amount didn't match what we saw in stars and galaxies. Discovering this hot, diffuse gas solved that. It was hiding in plain sight, in the spaces between everything. It completes the Baryon cycle, from smooth primordial gas to collapsing clouds that form galaxies, to explosive feedback that reheats it. Ready for the next cycle, to see the true cosmic web, you don't just see the glittering nodes, you see the glowing sea that connects them. These filaments are the real highways of the cosmos. The web is like a tapestry, and these are the woven strands. They aren't solid things, they're flowing rivers of influence, long corridors where gravity has pulled matter from the empty spaces around them. One filament can be hundreds of millions of light years long, but only a few million light years thick. Imagine a strand of spider silk, but scaled up so its length crosses our entire local supercluster, while its width is just the distance to our nearest galactic neighbor. That extreme shape defines what they do. They're conduits, cosmic aqueducts, channeling the universe's raw material from the barren voids toward the busy centers, the galaxy clusters. What moves along them? It's a mix of what we see and what we don't. The main part, as usual, is dark matter. Its invisible gravitational pull shapes the channel itself. Then there's the hot, diffuse gas, the intergalactic medium, the baryonic fog between everything, and then the galaxies. They aren't scattered randomly inside the filament. They're strung along it like beads on a string or towns along a river. That alignment isn't an accident. They formed there because that's where the material collected. That position is everything for a galaxy's story. To live inside a filament is to be plugged into the cosmic supply chain. Simulations show the dynamic environment. Huge rivers of cooler gas stream along these filaments, flowing toward the galaxies embedded in them. That's a primary way galaxies grow, through steady, cold accretion from the web. But it's not a peaceful trip. The filament is also a place of frequent, gentle encounters. Galaxy interactions happen more often here than in the isolated voids. Those gravitational nudges can compress gas clouds, triggering star formation, or slowly distort a galaxy's shape over eons, so the filament is more than a backdrop. It's an active participant. It provides the fuel and often the spark. A galaxy in a dense filament will have a different history than a lonely one in a void. It'll likely be richer in gas, more active in star birth, more shaped by its neighbors. The filament is the dynamic link between the profound emptiness of the voids and the intense crowding of the clusters. It's the cosmic intermediary, processing and transporting the matter that builds the visible universe. To understand the web, we have to study these threads. Astronomers now probe their specific properties. How thick are they? How does the gas density change from the filament's tenuous outer edges to its dense spine? Some observations even suggest these vast, thin structures might have large-scale magnetic fields woven through them, like threads within the thread. Each detail shows the physics of transport and structure on the grandest scale. These filaments are the great delivery system of the cosmos. By reading their conditions, we learn how the universe built its cities of light. The cosmic web changes structures. It doesn't just build them. The clusters we see now, these quiet, red cities of old stars, they weren't always like that. They have a history, and you can read it in the color of their galaxies. There's an observation called the Butcher-Oemler Effect, when astronomers look at very distant clusters, which means we're seeing them as they were billions of years ago. Those young clusters have a much higher fraction of blue galaxies. Blue light means hot, young, massive stars. It means those galaxies were forming stars. They were active, but nearby clusters, modern ones, that blue glow is mostly gone. They're dominated by red galaxies. Star formation has stopped. The clusters have grown quieter, redder with age. That shift in color tells a story of galactic life and death, driven by the cluster environment itself. Think of a spiral galaxy. It's out in a filament rich with cool gas clouds. Its gravity pulls it slowly toward the dense cluster at the filament's end. And when it finally enters the cluster core, it plunges into a different world. The space between galaxies in a cluster isn't empty. It's filled with an extremely hot, thin gas, the intracluster medium, and as the galaxy moves at tremendous speed through this superheated fog, it experiences a violent cosmic wind. That's ram pressure stripping. The pressure of the intracluster medium acts like a powerful gale. It blows the galaxy's own cool gas reservoir right out. That gas is the fuel for future stars. Without it, star formation grinds to a halt. The existing massive blue stars burn out fast. They leave behind the longer-lived, cooler, redder stars. The galaxy is quenched. Its blue spiral arms fade. It transforms into a red, featureless elliptical galaxy. But that's not the only force. In the crowded cluster, galaxies also experience frequent gravitational encounters. Close passes that can pull and twist them, disrupting their structure, funneling gas into their central black holes, which then blast out energy, further heating any remaining gas. This combination, ram pressure stripping and gravitational harassment, it efficiently shuts down a galaxy's star-forming engine. The Butcher-Oemler effect is the direct evidence of this process. It shows clusters weren't born looking as they do today. They assemble over time, and as they do, they fundamentally alter the galaxies that fall into them. The blue galaxies we see in the distant clusters are the progenitors of the red galaxies we see nearby. That links the largest scales to the fate of individual islands of stars. It shows how the architecture of the cosmic web doesn't just arrange galaxies, it engineers them. The journey along a filament into a cluster node is a galactic rite of passage, one that typically ends the era of star birth. By reading the population of galaxies within a cluster, you can deduce its history, its age, the violence of its assembly. The red glow of a modern cluster isn't a sign of stillness. It's a monument to the transformative power of the cosmic environment. For a long time, there was this accounting error in cosmology. The universe's books didn't balance. Our best ledger comes from the Big Bang. In those first few minutes, nuclear reactions made the lightest elements hydrogen, helium, lithium. The exact amounts depend on the total density of normal matter, the baryons. That gives us a very firm number for how much ordinary stuff should be out there. But when astronomers added up everything they could see, all the stars, all the galaxies, all the cold gas clouds, the total came up short by about half. Where was the rest of the normal matter? That was the missing baryon problem, a big gap in our inventory. The answer probably wasn't in the bright spots. It was in the highways. Theorists had suggested for a while that it was in the intergalactic medium, but not the cool gas we could map. They predicted a different phase. A warm, hot intergalactic medium, the WIM, picture that diffused cosmic fog, but heated to incredible temperatures between 100,000 and 10 million Kelvin. At that heat, the gas ionizes, electrons get stripped from atoms. It doesn't absorb light in ways we can easily see. It becomes nearly transparent, and it's exactly where the models said it should be, spread through the low-density filaments of the cosmic web and in huge halos around galaxy clusters. This is where feedback does its final work. The energy from supernova, the jets from supermassive black holes. That energy doesn't just stay in the galaxies. It pumps out into the web. It heats enormous volumes of that primordial gas. The gas doesn't vanish, it changes state. it becomes this hot, diffuse whim hiding in plain sight. Finding something that doesn't emit light easily is a profound challenge. It meant looking in different parts of the spectrum. X-ray telescopes were key. At those temperatures, the whim should glow faintly in X-rays. Astronomers also looked for subtle absorption signatures in the ultraviolet spectra of distant quasars, searching for the fingerprints of highly ionized oxygen. The hunt was painstaking, like trying to spot heat shimmer above a distant road, but slowly, evidence accumulated. Observations from telescopes like XMM Newton and Chandra started to detect the predicted X-ray glow from the vast filaments connecting clusters. They saw the absorption lines from ionized oxygen in the quasar spectra, right where the web was predicted to be. The missing matter wasn't missing, it had been found. This did more than solve an accounting puzzle. It validated our whole story of cosmic structure. The models predicted that violent feedback would heat and distribute baryons into this hard-to-detect state. The observation of the whim confirmed that. It closed the baryon cycle, so now we have a coherent picture. From the smooth primordial soup to the collapse into galaxies, to the energetic feedback that reheats and redistributes a large portion of the material back into the web. Where it waits for the next cycle of construction, the ordinary matter of the universe isn't lost, it's transformed, woven into the hot, invisible fabric of the cosmic web itself. Completing the architecture we are only beginning to truly see. Gravity builds the cosmic web, but there might be another force at work, a kind of cosmic magnetism. These fields are incredibly weak, 1 billion times weaker than Earth's, but they could be everywhere, in the voids between galaxies, woven right into the web itself. Where they came from is a puzzle. Some ideas say they started in the early universe, from quantum fluctuations stretched by inflation. Others think they came later, from the turbulence of the first gas or from jets from active galaxies. However they started, the process of building the web probably made them stronger. As gas flowed along the filaments, collapsing and swirling, that motion could have acted like a dynamo, twisting and amplifying those faint seed fields over billions of years. If they're really there on that scale, their influence could be deep, subtle but deep. They might guide high-energy cosmic rays, bend their paths across huge distances. Inside the filaments, magnetic pressure could offer a tiny support, a counter to gravity's pull, helping shape how thick and stable those threads are. And when that magnetized gas finally falls into a galaxy, it could affect how clouds collapse, how stars form, adding another layer to the birth of solar systems. So we're looking for a ghostly fingerprint on the largest structures we know. Detecting a magnetic field across 1 million light-year void is incredibly hard. Astronomers have to look for indirect signs, whispers in the data. One clue is synchrotron radiation. When high-energy electrons spiral along a magnetic field, they emit a specific radio wave. Finding that diffuse radio glow along a filament would be a smoking gun. Another method uses Faraday rotation. Light from a distant quasar passes through a magnetized region, and the field twists the light's polarization. Very slightly, by measuring that twist across many lines of sight, we can map the presence of these vast fields. Statistically, this search adds a new dimension. The cosmic web might not just be a sculpture of dark matter and gravity. It could also be a canvas for electromagnetic forces, painted with strokes of primordial magnetism. Confirming it would show a universe more richly textured, more interconnected. It would mean the empty spaces aren't truly empty. They're threaded with invisible lines of force. A silent energy that's been part of the story since the beginning. Light is just one way the cosmos speaks to us. Modern astronomy listens to other messengers too. Two of the hardest signals to catch are neutrinos and gravitational waves. These aren't light, they're different carriers of information coming from the most extreme events. And they're starting to tell us new stories about the hidden life of the cosmic web. Neutrinos are ghostly particles. Trillions go through you every second, leaving nothing behind. They have almost no mass, they hardly interact. That makes them incredibly hard to detect, but it gives them a unique power. They can travel straight from the heart of a cataclysm, a supernova, a quasar's jet, colliding black holes, across billions of light years without being deflected. Without being absorbed, the ones we hunt are the ultra-high-energy cosmic neutrinos. They come from the most violent accelerators in the universe. When we catch one and trace its path back, we're pinpointing a location of immense energy release. If many of these events cluster along the predicted filaments of the cosmic web, that's a new kind of map, not a map of mass, a map of fury. It would show us where the web is most active, where its gravitational engines are driving matter to collide and explode in ways light alone can't fully reveal. Then there are gravitational waves, ripples in spacetime itself. We detect them from mergers of stellar mass black holes and neutron stars, but there's a deeper signal we're searching for. A cosmic hum, the stochastic gravitational wave background from mergers of supermassive black holes. Every massive galaxy likely has one of these monsters in its core. When galaxies merge along the cosmic web, their central black holes eventually spiral together. That process, happening countless times across history, creates a faint, omnidirectional rumble. It's not a single chirp, it's a background murmur. Future observatories like space-based laser interferometers aim to hear this hum. Why does this matter for large-scale structure? Because the history of supermassive black hole mergers is tied to the history of galaxy mergers, and that is the history of how the cosmic web assembled itself. By measuring this gravitational wave background, we could infer how many of these giant mergers have occurred and when they peaked in the universe's timeline. It would be an acoustic record of the web's construction phase, written not in light but in the vibrations of spacetime. This doesn't show us the web's shape directly. Instead, it tells us about the dynamic processes that shaped it from within. That's the promise of multi-messenger astronomy. We're no longer just watching the universe. We're feeling its vibrations and catching its ghostly particles. Light shows us where the matter is. Neutrinos point to where it's being torn apart. Gravitational waves tell us when its heaviest components crashed together. Each messenger fills in a part of the story the others can't see. Together, they're building a richer portrait of the cosmic web, not as a static sculpture, but as a living, breathing architecture. Sometimes violently energetic, mapping the universe's largest structures, it's something humans do. It's not just science. The tools we use to see it, the space telescopes, the supercomputers, the big digital sky surveys, they're built by groups of countries. They're funded by societies that decided to put money into a question that doesn't give any immediate material return. To put those resources there, brilliant minds and advanced engineering, toward understanding our place in the cosmos, that's a statement of values. It says, as a civilization, we care about the story. We're willing to look past our immediate horizon, to ask questions that will outlive us, for a perspective that ties all of humanity to one shared origin. There's a paradox in it, a beautiful one. We're temporary, we're on a speck of dust, and yet we have the mind to not just see the immensity around us, but to measure it. To model its history, to project its future. We can hold the idea of 1 billion light years in our heads. We can trace cause and effect over 13.8 billion years. That ability for abstract thought, for long-term inquiry, it might be what defines us most. Decoding the universe is the ultimate use of that ability. It forces a kind of humility, not a shrinking kind, an expansive kind. It redefines home. Home isn't a street or a country. It's a galaxy inside a supercluster, inside a web that spans everything we can see. Now the details: Baryon acoustic oscillations, warm, hot intergalactic gas. They can seem detached from daily life, but the cultural impact of this knowledge is deep. It fuels our collective imagination. It makes kids look up and wonder. That sets them on paths of discovery, and those paths lead to innovations in medicine, computing, engineering. The drive to build a telescope like Euclid or Vera Rubin pushes the boundaries of what's possible. It creates new capabilities that ripple through our whole technological world. And more subtly, this cosmic view gives us a unifying story. In a world often split by borders and beliefs, the cosmic web is a reminder of a deeper, shared heritage. Every person, every nation is under the same ancient sky, inside the same grand structure, born from the same primordial seeds. So this search to understand the universe's architecture, it's more than collecting data. It's an expression of human curiosity, of resilience. It's a testament to our persistent need to find our place, to read the story we're part of, to understand the forces that shaped us. We are the universe's way of knowing itself, and by tracing the great walls and filaments, we are slowly learning our own address in the story of everything. It started with a whisper, a quantum flicker stretched out by inflation. Gravity took those seeds and spent almost 14 billion years building something. The cosmic web, we've traced it from the first ripples in the Big Bang's afterglow to the billion light-year walls, the largest things we know. Dark matter shaped the first valleys. The invisible skeleton and ordinary matter, the baryons, flowed into those valleys. That's what lit up the filaments, the galaxies, and then there's dark energy. The force that will unravel it all. Its push will stretch the web into silence. These structures are more than landmarks. They're laboratories. Their immense scale lets us test the laws of physics. The Great Walls stress our idea of cosmic homogeneity. How clusters are distributed shows the tug of war, gravity against dark energy, and the faint, hot gas in the filaments holds the missing ledger. The ordinary matter we haven't accounted for. Every new map is an experiment, asking what the universe is made of, how it came to be. They tell our story too. The atoms in this planet, in us, were forged in stars that ignited because of this web. The same gravitational currents that sculpted the Sloan Great Wall guided the cloud that became our Milky Way. We're not just observers, we're products of it. Studying the largest structures is investigating our own cosmic ancestry, a lineage written in light and gravity. Now new eyes are turning skyward. The Vera C, Rubin Observatory, Euclid, the Nancy Grace Roman Space Telescope. They'll map billions of galaxies, trace the web in detail we can't really imagine. They'll measure the dark universe with a precision that could confirm our models or reveal cracks, point toward new physics. The universe's greatest mysteries are often its largest. What other titans are out there beyond our maps? Could there be structures that redefine scale itself? The search continues to find our place in the story, to understand the grand design we're a part of.